in this section, we're just going to talk about the sort of the theory and some of the important settings behind the flip solver so that we can put the right parameters to use for us in creating our own flip simulations later on. We're mostly going to be exploring just the shelf tools and making, just kind of dissecting what they present us in terms of setup. And then we might make some modifications to them just to see how we can kind of modify them and bend them to our will. So I'm going to start here with the in the build layout. So I'm just going to select the build layout from up here. And we can just throw down some test geometry. I'm going to throw down the pig head. So test geometry, pig head. And we're going to turn this pig head into a blob of liquid and drop it. So I'm going to bring it up a little bit like this. Maybe right. Yeah, 3 seems good. Maybe we'll just do 4. Bring it up to a height of 4 meters. And then I'm just going to hit up here on your shelf. If you go to the particle fluids tab, you got this flip fluid from object shelf tool. So let's just click that and see what happens. You can see that it has turned our pig head into a bunch of little points. And if I click play, they fall down. And they also change color depending on how fast they're going. That's just a visualization option in our flip solver that helps us see faster moving particles. And it makes the sim a little bit easier to understand, I think, as well. So let's take a look at what this has done for us. If we go back out to the object level, you can see that it's taken our test geometry pig head. It's created an auto dop network for us, which holds our flip sim. Then it has created these 2 nodes, which is the test geometry pig head 1 fluid. So I jump in here, you can see this is a little area where we export or we import the data from the dop net, and then we can do some surfacing operations. We can cache it out, turn it into a volumetric surface like this, or sorry, a polygonal surface like this. It's pretty low res, but you can create your fluid surface from your particles in this section and then cache that out as well. Then the last one that it creates down here, it actually pulls in information from the fluid surface and uses this to render. Now, what is it doing in this? We've got this other fluid surface here that we could be rendering. You can see if we look at the render tab, there is actually a basic liquid material applied here. But what this one's called the fluid interior. This one is actually going to do, it's going to use a special uniform volume shader. This is a mantra shader that will actually fill a polygonal surface with a volume-like material. So it's basically computing at render time a density, a fog density that would fit inside of that geometry, and it creates a really cool looking subsurfacey type of an effect when you actually don't apply subsurface to the liquid itself, but you actually stick a volume inside of it. You get these insanely cool looking results. We're not going to really explore that too much in our examples here, but just know that that's there. And if you wanted to, you could just actually just take this and convert it to a fog VDB and export that as a VDB if you wanted to, and render it in Redshift that way. So these are the nodes that are created for us. I'm going to just name these all something that makes a little bit more sense. So here we've got our source. The pig head is where we're going to be sourcing and determining what is actually going to be making our particles. Then our Autodop network, this is going to be FlipSim. FlipSim, and this is going to be the import fluid, and then this will be the fluid interior. I'm just going to delete all that stuff. So now this sort of is a little bit less wordy, a little bit easier to see. So the next thing I want to do here is, because the sim is pretty boring, it's just gravity. I want to add a collider. So I'm going to just hop back up here. Maybe between the source and the flip sim, I just like to kind of organize my things so they go down the chain in order, almost as if they're connected, but not really. In here, I'm going to throw down a torus. And this is just going to be our collider. And I'll bring this one up a little bit, like maybe up to a value of 1.5. Looks good. So it's going to drop. We're going to drop the fluid, the pig head fluid, onto this torus. And to get it into our sim, I'm going to just grab the collider. I'm going to go up to the collisions tab, and I'm just going to select a static object. And when I go inside the collider now, you can see that, you know, initially we just had this torus right here, but after we click this static object, what the shelf tool has done is it's looked and it saw that, okay, over in our DOPNet, we're doing a fluid simulation, and it has made a determination for us what the best type of collision is going to be. And here, that would be using a volumetric collision. So this collision source right here will actually create a collision volume for us, and it will it gives us the opportunity to cache it out if we want to. We don't really have to, because it is pretty much, it's low res enough and it isn't deforming, so we don't really need to cache anything here. So we can just I can just bypass this file cache. It's not really doing anything either way since load from disk isn't on, but just to, you know, make the point that we don't really need it right now, I'm just going to bypass that. But if we go over here, you can see that it's created a VDB for us that we'll use as our collision object with flip. And then this is just a sort of a node for the DOP simulation to look up the actual geo that's going into it. So I'm going to just leave this display flag back on the torus, and then I'm going to just disable that and go back to the flip sim. So now inside our flip sim, you can see that it's created this stuff over here. I'm just going to hit the L key to lay that out a little bit better. And you can see that it has created this collider object right here for us, which is bringing in that that node that it created in the other geometry. Now, this SOP path is actually pointing to geo that is not a VDB. It's pointing to this attribute create that it created over here, which is just the dot path. So because it is oops, sorry, I'm going to go back to the flip sim. Because this collider is actually referring to, you know, non-volumetric data, basically what that is just so that we can display the geometry in our sim. What it's actually using for collision, if I go down to this collisions tab, scroll down, what it's actually using is it's doing this volume sampling operation here. And this volume sampling is looking up that collider VDB that we were just looking at. So now, when I drop this pig head and hit play, it will collide with our torus that we created. And you can see that it kind of splashes around and gets all liquidy looking down here. It's still a pretty low resolution sim, but it continues on and does its thing, which is cool. So now let's go over some of the settings that we've got. Most of the settings that we're going to do that really influence the look of our simulation, they occur on the flip fluid object and the flip solver. So let's start off with the flip solver. We're just going to go through some of these tabs and kind of get these things out of the way. So substeps in general, you know, for our purposes, these are going to be fine the way that they are right now, but in some instances you'll want to increase substeps to get a more accurate simulation, but for what we're doing, it's not going to really matter at this point. Let's go to the next tab, the particle motion tab. You can see actually we've got this particle motion tab and the volume motion tab. And these are the particle motion and the volume motion are those two aspects of flip that it's the hybrid solver where it's doing a particle sim and then it's doing a volume sim. And these are the two tabs that control how that sim is being modified. These are the parameters that we can use to modify the different aspects of those two sims. So under particle motion, you'll see we've got a couple more tabs down here. It's just sort of like a subsection down here. So under the behavior tab, we've got all sorts of options like adding friction and bounce, adding IDs, which I certainly like to do when I'm working with particles, because having an ID attribute on my flip particles will allow me to do things like randomly delete them without them changing, because a lot of times in flip sims we have changing point counts. So if I wanted to add an ID attribute, I could do that now. I could add friction and bounce. Adding friction and bounce will actually allow the these physical properties of the it actually will activate some of these physical properties on the flip fluid object. I'm going to actually turn it off for right now, but having an ID attribute is actually super important when you get into stuff like reseating. So this next tab, reseating, what happens with reseeding is basically what Houdini is doing is it's adding or removing particles from the simulation to achieve a certain like spatial density. It makes the particles more evenly distributed throughout the space represented by the fluid, and it can be really something that you want to do in some certain situations. For really high viscosity sims, which basically means like goopy stuff like ketchup, sometimes receding with really low settings can actually lead to flickering. So you may want to crank up surface oversampling is one trick to actually get smoother surfaces, or you could just turn it off in general. If you disable this, then no particles will be added or removed by the receding. Obviously, if you have an emitter, it'll be continuing to add particles, but leaving this off, it won't reseed and redistribute particle like the particle spatial relationships throughout the simulation. So we're just going to leave that on for right now. And then let's look at separation. Separation is off by default, but what separation is trying to do is kind of, it's not necessarily removing particles to achieve a uniform distribution. It's actually pushing the particles apart by doing kind of a relaxation process. So it's off by default, and we're going to leave it off for right now, but it can be helpful when you're trying to do things like filling up an object with fluid and other things like that. So this other tab right here, droplets, this is basically this droplet section allows us to basically tell Houdini what it should do with stray particles that have flown away from the main body of the fluid. You can kill them, blend them with fluid, all that stuff. I generally don't mess around with this too much, but it's there if you need it. And then there's the vorticity. The vorticity is basically, it talks about how to deal with spinning motion inside of our simulations. And then rest is what we would use to add rest attributes to our simulation so we could stick UVs onto it later if we wanted to. These things are a little bit beyond the scope of what I'm trying to accomplish in this mini lesson in Flip for right now. So we're going to just leave most of this stuff just the way it is default. So the other thing is in the volume motion. The volume motion, now that we've talked about different ways we can modify the particle motion, the volume motion is where I feel like a lot of the interesting stuff happens. So this is going to handle things like collision behavior, viscosity. If you have density mixing, it's going to do that here as well. Also air for like air incompressibility in case there's like little pockets of bubbles inside of the sim. It can mess around with those. Divergence is basically also just a field that is like representing expanding or contracting forces inside of the sim. Surface tension, so you get really tiny little, you can simulate really microscopic water droplets by adding surface tension, and then other solver options here. Now, because this solver is a volumetric, it is like basically like the pyro solver happening in the background. There is an opportunity to use OpenCL. I don't think it helps too much with Flip, but the option is there to turn it on. So sometimes, usually I'll actually come over here and just turn OpenCL on, and it will use the GPU to run a little bit faster. So let's go back to this first tab here and take a look at what volume limits are. So you can see when I click play and this pig head goes down, you can see that as this fluid sim spreads out, it's kind of hard to tell right now, but it's actually spreading out throughout this gigantic box here. This is more or less the domain of our simulation, and it will do that volumetric calculation for any particles that are within it. And then when they reach the edge here, they will leave the simulation and be killed. So we can actually change this. It's a little bit big for what we need right now. I'm just going to bring the box size down. So I'm going to middle mouse over the box size and bring it down to a value of, looks like a 10 by 10. That seems good. Maybe I'll go down a little bit more to a 7 by 7. That looks good. So the next thing I'll do is I'll actually do the same trick that I always do, which is I'm going to copy the box's height and paste it into the center Y. Say paste relative references. And I just want to divide that by 2. Whoops. So limit divided by 2. and that'll just rest the box on the ground. If I were to click the manipulator and click the flip solver, it also gives me controls where I can kind of resize it using these handles as well. But so this volume limits is basically a container for where the volumetric calculation is going to occur. Now we can change the way that the flip object interacts with these walls by going to the flip fluid object and ticking closed boundaries. The fluid will no longer flow out of this simulation, but rather it'll use these walls as colliders. And we can actually change what happens with each one of these. We can actually say, oh, I want it to actually keep the floor as a collider, but if it flows out of the sides, so plus X and minus X and plus C and minus C, that means it'll flow out of the simulation. So if I click play again, you can see it collides with the ground, but once it meets the edge, they're all killed. So that's just kind of a cool thing that you can use to get some pretty cheap interaction. Like, for example, I could have thrown down a ground plane so that these particles would collide with the floor, but I've got this this volumetric calculation that's kind of going to deal with the ground plane for me. So I'm just going to turn all these closed boundaries back on for right now. Now back on the flip solver, so if we go into collisions, obviously we have collision settings that we can control here. I'm going to leave those at default, but I do want to look at viscosity. Viscosity is pretty cool. We can actually enable viscosity. And then if we go to our flip fluid object, we can set our viscosity here. So this is one of those things where a lot of the settings that are in simulations are actually, they're in a couple different places that you got to go to get them to activate. But just, you know, you eventually get used to it. Okay, you want to turn on viscosity on the flip solver. Well, that's a volume calculation. So we're going to enable it here. Then we're going to go back to our flip fluid object and we can supply some viscosity to it here. So I'll put in something like 100. And then if I hit play, you can see that we get a much goopier sort of result. Now this sim is pretty low res. I'm going to see if I can bring it up a little bit. I'm going to just take so the really important, most important factor in terms of quality of your simulation is this particle separation on your flip fluid object. So I'm going to just bring that down to a value of 0.05, and you can already see that the density of our sim is much more closely representing the shape of the pig head, and we're starting to get much more interesting and realistic looking results from it. So the other one that I kind of want to try out here is on the flip solver. I'm going to turn off viscosity. So if I hit play, our pig head should just come collide with the collide with this, and then it gets very splashy and turns into this gigantic sort of tank, if you will, that is full of liquid that came from the pig head. Now, there are different types of kernels that handle this thing. So up here, you can see that the velocity transfer here is using splashy kernel. Splashy kernel is a setting that is really good for like large scale simulations. It creates lots of little water droplet like things that just look very splashy, you know. Very descriptive name. It's good. So the other one is a swirly kernel, and I might use the swirly kernel if I was trying to do some more viscous stuff. But if I play it back, you may or may not notice that much of a difference with how this motion is working. I mean, it seems pretty close to the previous simulation, but you can see it's almost like it's adhering a little bit. It has much more like almost larger features. So sometimes if I'm doing a viscous sim like we had before here, I might want to use the swirly kernel. I might get a better result with that. It's just a matter of trial and error and figuring out what it is that what it is that suits your simulation needs. So with that, I'm going to turn viscosity back off. I'm going to go back to the splashy kernel, and then let's just look at this surface tension over here. Surface tension is really cool. Like I was saying when we briefly went over it, but basically it allows you to simulate like very tiny water droplets that are undergoing surface tension that wants to make them adhere to one another in like sort of a spherical type shape. So if I turn on surface tension, well, first off, like I'll go on the surface tension tab. I'm going to just disable gravity for 1 second. And if I click play, nothing should happen. So your simulation is more or less just frozen particles in space. But if I turn on surface tension, you can see that it sort of starts to act the way water would if it were actually floating in outer space. So it's kind of not obvious right now, but I'm going to turn this up to a value of maybe 1,000 just to see what happens. And you can see that it pulls all that liquid in, and it's trying to keep it, it's trying to get those particles to sort of adhere to themselves in a way that conserves energy. So it's becoming more and more spherical. Now if I were to turn gravity back on and drop this, so I click play, you can see that it comes down. We still do get like sort of a splashing like effect. The water is allowed to separate from itself, but you can see that you're getting many more of these, like if I pause here, you're starting to get more of these like nice like tendrils that come off, and you can see that it's starting to like suck. The particles are starting to almost like attract themselves back together all around the edges of this sim. And if you of this tank, and if you kind of let it play back for a little bit, you can see that how this actually would feel much more small scale. Now, obviously, like getting the scale of your sim down is a thing in and of itself. Certainly, if I was going to be simming really small particles, I mean, a lot of times what people will say is that you want to simulate at the real world scale that you're going to be working with. I don't find that always to be like the best way to go. I feel like Houdini works the best when we're in like the range of from like a meter or so, or like within 1 to 10 meters. So a lot of times what I'll do is just kind of cheat it to get it to behave more like a water droplet. So if I wanted this to be like to really act more like a water droplet, what I might do is decrease gravity. So we're pretending that we're like at a smaller scale. I'll just bring this down by a factor of 10 and then play it back, and then it should with less of a gravity force, it should start to really kind of feel much more like we're working at a very, very tiny scale with our simulation. You can really see how changing that gravity has actually made this all pool up and sort of tendrilize much quicker, all while seemingly going in slow motion. So that doesn't seem like it's going in slow motion. It only seems like it's going in slow motion because you're simming it and your computer has to think pretty hard about it. But so you can see how those different kinds of settings can get you some pretty cool looks. If we just play this out a little bit longer, you kind of get a sense that it's doing like the liquid metal kind of thing, like mercury almost on the ground, which is kind of cool. So if that's sort of like the effect that you're after, surface tension is one of the ways that you can get there. It's just kind of neat. Ew. Cool. So I'm going to turn surface tension off for right now. And let's just look at some more settings on this flip fluid object. So let's go over to the initial data tab. Over here, this is sort of like what we encountered in POPs, where we kind of defined how it's actually going to create the initial data for our flip fluid object. So if we go back here, you can see that it's looking at our object source that we created out when we made our pig head, and it is looking at a surface stop right here. Now we could change this to, we could supply, and it's built, it's basically filling that volume or that object with particles, but we could actually supply our own particles if we wanted to with our own attributes and have them sort of inherit into the simulation. That way we could drive the input on our own and not let this solver kind of come up with it on its own. So this is where we would do that. So for example, if I actually wanted to do back out here in our source, if I wanted to supply my own particle field, I could do that. I could say, let's do points from volume. And if I wire this here, you can see that it creates a little grid of particles for us inside this pig head. And we could just change, what we want to do is we want to actually match the density of these particles to our flip simulation. We just go over here into our flip sim, look at our flip fluid object, and this is where we're setting this particle separation. We want that to match. And you'll see that a lot of other flip setups will do this. We'll just right click and copy parameter. And then we'll go back over to our source. And then in point separation, which is the same as particle separation, we'll say, I'm going to select all of this and right click and say paste relative references. And for whatever reason, it adds this .0001 to the end. I'm just going to delete that, enter. And now it has filled that pig head with points that are all kind of uniformly distributed. That's where this other thing comes in, jitter. So the jitter scale, if we crank this up to 1, we're going to get pretty close to what we had over here in our flip sim. So now the flip fluid object was looking for a surface. We just supply it now with a particle field, and we're back to where we were in the beginning. We supplied our own particle field, and it's doing its thing, which is awesome. So the cool thing now about supplying your own particle field is that you can send attributes in a lot more discreetly into your simulation and have them take effect, which we'll do in just a couple minutes. I just want to go over a couple more settings on the flip fluid object before going too far with that. And that is like here, you could see in our initial data now, if we wanted to add a viscosity attribute, we could do that. We could add temperature, divergence, etc. We could also add initial velocity if we wanted to. Here, if we wanted to just add some velocity to our particles, we could do that. So that's all good to know and keep in mind. And so in the next one, this section, the guides, you can see that we're actually able to visualize different parts of our simulation. So by default, we just have particles turned on. And so all these checkboxes kind of turn on and off different aspects of the simulation visualization. And then you control those visualizations with these different tabs that we have over here. So for example, if we wanted to visualize collision, I could go to this collision tab. It's not enabled. So if I went back to the visualization tab, ticked on collision, you can kind of see there's a little representation inside of here in purple of this geometry that we have. So if I go over to the collider and just say I'm going to turn off display geometry, you can see now we're visualizing the collision in this simulation. And we could do other things like visualizing the surface, and it just gives us the rough surface that's being used in the volumetric calculation, and all sorts of stuff. Pressure, density, would just create like a slice. So some of these things can come in handy. Generally, I just like to use, I just keep it with particles for the most part, unless I'm trying to debug something with my collision or whatever. So under the particles tab, we can actually change the visualization type. Sometimes it's kind of fun to use sprites, but they can get pretty heavy. Sprites basically is just like instancing a little image of a sphere on there. And if I just dial the scale down, we can kind of get something that looks pretty cool. But I've found that with really high res sims, it doesn't, it ends up kind of slowing things down a lot because it's, I think, a little bit harder for OpenGL to write all this stuff onto the screen. So that's there. You could also do particle. That's what we were doing. We could do spheres. And so it instances little spheres on there. I feel like that may or may not be even faster or slower than other stuff. So kind of, you know, beware if things are running really slow. Maybe it's your visualization needs to be set to particles. So I'm just going to set ours back to particles. And then down here, we've got this visualization type set to speed, which is cool. Basically, it's almost like kind of a fake whitewater sim. So, you know, faster moving particles are going to get whiter. But we are using this velocity attribute we had and just remapping it to this range right here, which we can change. If I wanted to make it get whiter faster, we could just shrink that down, or we could actually just extend the range of our visualization. So if I just shrink down the visualization range to something like 2, you can see that it goes to white much faster. Basically just clamping it down, so it's going and getting super white very quickly. So that's just a little bit of a look into what these visualization settings are doing. If you don't want them on at all, you could just say none. I want to visualize the particles. I just don't want to see any of the colors. You just turn that off. That's if that works for you. I'm just going to leave it back on at speed for right now. Other properties on the flip fluid object, let's go over to the physical tab. So we kind of went in here when we turned on viscosity. So we've got this viscosity attribute, and we've got this bounce and bounce friction, scale, and all that stuff. So these different friction attributes, you can try and turn them on. I generally don't really mess around with them too much, but if you wanted to enable this, you wanted to turn on friction, for example, I'm just going to crank friction up to 1. And you'd notice that, like, if I got to turn my collider geometry back on. If I were to play this back, it's not actually going to incorporate any friction into our particles because it hasn't been enabled on the flip solver. Like we saw earlier here in our particle motion behavior, there's this friction and bounce attribute. So if I were to turn that on, it would affect the way our simulation works. And then I guess I could go and maybe in our collider here, turn on under the physical tab of our collider object, I could crank this friction. Looks like it's already cranked up. I mean, I could crank bounce up. I could go over here and turn the bounce on my flip particles up, but now we're going to get, I think that now that we've enabled this, it's generally not a result that we really want. It starts to look less like actual water, but if that's what you're looking for, that could look kind of cool. I don't know. I mean, maybe if we combine this with some sort of surface tension, that could look pretty cool, but you can see how these different sort of particle properties influence our simulation if we want them to. So if we go back to the flip solver, I'm just going to turn off friction and bounce. They're there, but now they're not going to actually affect the simulation, even though we have set them out here on our flip fluid object. And it looks like actually something is going on with it. I'm going to hit the escape key. You can see all these particles just blasted off into forever. I'm going to turn off bounce on the flip fluid object and just bring friction down to 0. And also over here on the collider object, I'm going to bring the bounce down to 0. Or what was it? I think the default's 0.5. Yeah, default's 0.5, or you could right click and say revert to defaults here. So now if I go back to frame 0 and click play, once we make contact with the torus, everything should be back to somewhat, yeah, everything's back to normal. So that's cool. All right, back to the flip fluid object one last time. This last tab for collisions this allows you to determine what types of velocities being calculated to determine collision, and I generally just leave that at default too. Cool. So now let's try and do just a little quick kind of variable viscosity on this thing. We're going to make this, what we want to do is we're going to drop the pig head on the torus, but I want the pig head to have sort of areas that are really chunky and thick and viscous, and then other areas that are very liquidy and melty. And you can see if we just modify some viscosity attributes coming into our sim, we can get some pretty cool looking results. I think that this torus is a little bit big. I'm just going to hop over to, I'm going to turn on the source and the collider and just hop into the torus, and maybe I'll bring it down a little bit in uniform scale. Let's make it a little bit smaller, something like that. It should be good. And then what I'll do is we'll go over to our source. So now that we've created these sort of particles, it's kind of important to note. Now, if I were to go back and select the pig head and go back to my simulation and click play, now it's dropping particles from the geometry surface. Like, what's the deal with that? This is just sort of an important thing to note when dealing with the shelf tools, is when we created our flip object here, it initially was looking at the SOP path. The SOP path is actually in the geometry context. It's not actually looking at a null or anything inside of our source. You can see our source is out here. It's just looking at whatever this node is. So whatever the display flag is inside of this node is going to affect what it's actually looking at inside the sim. So to prevent any confusion like this from happening, what I generally tend to do is throw down a null at the end of this and then explicitly have the source look at this null. So if I put this null and say source particles, and then I go back up here, I can set my display flag to whatever I want inside this network. And if I go over to my flip sim in my flip fluid object, and I point the SOP path to that null instead inside of our source here, the source particles, hit accept, go back to frame 0. Now I can, if I just hide other objects, now even though up here on the object level I've got my actual pig head being displayed, because we pointed this to that null, because we pointed our source to that null, we still get our particle source, which is cool. So it's just something to make note of if you're doing sims and then you change something and all of a sudden, like, now we got this happening. Well, that could be why, is because it's looking for object level sources when really we want to be, you know, explicit about what's happening inside of here, you know, and have it look up a null at the end of our chain. So let's get back to this and create some additional attributes here. So what we could do is we could actually modify the viscosity attribute on our simulation. So let's do that using a point fob. And we're just going to throw some noise into these particles and use that noise to determine what our actual viscosity range should be. So because we're messing around with attributes, I'm going to go up here and say split pane top bottom, and I'm going to right click on the scene view and click on the geometry spreadsheet so that we can actually have a view of what our noise ranges are and stuff like that. So inside the point fob, let's create a noise. I'm going to throw down a anti-alias noise. I just hit tab and started typing AA, and it's one of the first things that come up when you just type in AA, this anti-alias noise. So the noise, we're going to take a 3D input and create a 1D noise. That's good because viscosity is a scalar. It's just a value between 1 and 0 determining, well, actually viscosity's range is very high, but we just want to create a noise value between 0 and 1 in one dimension and then just remap it to some other higher viscosity value. So we're going to do that based off of the position. So we're going to wire in the position here, and then I'm just going to wire the noise out to color for visualization purpose right now. You can see that it makes the pig head a little bit some dark spots. Maybe I'll hit the D key and go to visual my background and turn it to light mode this time, so I can kind of see my lighter and my darker particles in the same space. So I've got this anti-alias noise. I could increase the frequency of that, and in general what I want to do is now kind of see, I want to kind of map this range out to viscosity. So let's throw down a bind export. And the attribute we want to bind out to is viscosity. So I'm going to type in viscosity here. And I'm just going to wire this noise value into that viscosity. Now if I look at my noise, or if I look at my color, since I'm also wiring this out to color, you can see the color attribute is just sort of more or less to visualize right now, but we can see that our viscosity is actually ranging from something like negative 0.45. If I just click this top column here, it helps me kind of sort it'll sort by the attribute value. So if I scroll up to the top, you can see that my maximum is 0.36 and my minimum is negative 0.45. So I think what I would do at this point is do a fit range. So I'm going to fit range my viscosity, and I want to take the source minimum from that value. So if I'm just going to shake that off real quick so I can see what that minimum value is. Minimum value is 0.45. So I'm just going to put my source minimum as 0.45, and my source maximum I'll set to something like 0.35. Oops, sorry, my source minimum to negative 0.45, my source maximum to 0.35. And now if I wire that in here, you can see our viscosity ranges from 1 all the way down to 0. Our output viscosity values of 0 to 1 are not very aren't very dramatic. I mean, viscosity of 0 is basically water, and then a viscosity of 1 is something just above water. But I want to get a little bit more extreme with it. So I'm going to take this, let's take this viscosity, the destination max, let's just set it to something like 1,000. And because we don't see any modification to the color channel because we're not using this fit range in the color channel, but we can actually map this out to viscosity separately, and it will, you can see our viscosity levels are ranging from 1,000 all the way down to 0. So now if we jump back over to our flip simulation, and we can play it back and see if those different chunks in our simulation are having any effect on the way the simulation looks. So hit play, check it out. Doesn't look like it's doing a lot. And I think that what that has to do with is the fact that we never turned it on. So here you can see in the flip solver, we've got our volume motion and we've got a viscosity tab. I want to enable the viscosity, and I also want to enable the viscosity by attribute, because that attribute that we determined before, viscosity, is labeled right here. And because those two values that we did match, you know, that bind export we created matches this viscosity attribute, we go back to frame 0 and click play. It should all start to work now. So now you can see we're getting much more viscous sim in our geo, but it looks like not much of it is actually low viscosity. It all looks like it's pretty high viscosity to me. So I think what I would do also is on this flip fluid object, I always like to add this viscosity attribute. I'm going to try and click play and see what happens here. Same result. I think really what's happening right now that we need to do is we need to sort of go and modify a couple things. So now in our physical, we still have this viscosity set to 100 in our physical tab. We should be overwriting this, but I'm going to bring this back to 0 just as a troubleshooting thing. So to make sure that the values that we're providing are actually taking effect. And you can see that it looks like that they are. We just need to modify that range, that viscosity range that we supplied earlier. So I'm going to go over here back to the source, and I'm going to just kind of clamp these values in a little bit more so there's more dramatic of a difference between our lows and our highs. You know, so I want really, what I want is like the white areas to be extremely there's a lot of if we scroll back, you can see there's a lot of gray area here between 0 and 1, and I want that to be, those edges to be a little bit more defined. So I can do that by kind of like adding contrast into our noise pattern. So I'm going to do that by, let's go over here. I'm going to actually split this out into a couple different fit ranges. So I want to create a new, I want to create a ramp. And to do a ramp, I need something that goes from 0 to 1. So instead of setting the destination min and max here, I'm going to actually split this out into 2 different fit ranges. So I'm going to throw down another fit range. And I know that what I can do is if I take this first fit range and I've set my min and max and I'm remapping it from 0 to 1, now I know that I could throw down a ramp here, a ramp parameter. And if I set this ramp parameter to a spline ramp, I now have a contrast curve that I can use to clamp those values. And if I just visualize this, you can kind of see what I mean. Now the ramp parameter doesn't work when you're inside of VOPs, but if we go back out here and set this to a sort of straight line, you can see that this is the effect that that ramp is having. Now if I bring in the bottom and tighten up the, oops, sorry, I'm just going to drag some of these away. Okay. And then I just bring this notch in towards the top. You can see if I shift select both of them, I can actually kind of change that the amount that's high and low viscosity. So maybe I'll just add a little bit more of the low viscosity stuff, which is the black. So now we've got pretty much pretty defined black areas and white areas and just a little bit of gray between. So now because we remapped that, it's still a value of 0 to 1, but it has much more contrast in it. And then we can use this second fit range as the one that we remap it from 0 to 1,000. So I'm going to crank this up to 1,000. And let's just go back to frame 0. I'm going to hop into our flip sim. And we're going to click play. And you can see that the areas that are black are dripping much more freely than these chunkier, viscous blue areas. And the reason why they're blue in this simulation is because it's actually doing some of this particle visualization stuff with the speed. So if I go to the flip fluid object and go to guides, and I go back to this particle visualization, turn the visualization type to off, we just get our original particles back. So now I'll click play, and you can kind of see that we're getting this nice sort of variable viscosity where these black particles are very free to move, but the white ones are very rigid and very goopy. So you can get some pretty cool effects by just kind of feeding in some simple attributes like that into your simulation, which is pretty cool. I'm just gonna rewind this simulation and play it down real quick until I get to a point where I've got some nice like kind of drips hanging off the side of our simulation here. Cool. So now if I go into the import node, you can see that I previously what it's doing is it's importing the data. So it's importing the geometry and the surface and velocity fields. And then by default, it's going to compress them. So then it creates this little kind of grid of compressed little pieces of packed fluid sim. And then at this point, we could cache it out to disk, and it would be a more efficient sort of cache, which is cool. But then over here, the next step we do, I'm not going to cache it just yet. The next step we get is this particle fluid surface node. And this node is probably one of the more, I mean, this aspect of fluids is so incredibly important. I can't even, there are many strategies for which to get like a really nice looking fluid surface from a flip sim. And a lot of those strategies are packed right into this node. You can see if you dive into this node, it's just a rat's nest of all sorts of different settings that they've extracted up to the surface for us. A bunch of different workflows we can use to get good looking results. So let's just look at what we get. By default, this looks like pretty garbage. You can tell it's pretty low res. These strands are pretty big. It just doesn't look that great. I mean, compared to even the original particles right here, you can see it's created a separate particle fluid surface for us that we can use to preview our actual geometry. I like to actually just, instead of particles and fluid surface, I like to just set it to particles so I can see the particles. I honestly feel like I can see what looks like a pretty cool fluid sim in these particles, but then when I turn on this particle fluid surface, it just looks like blah, So the reason why it's blue is it's using the texture from the object that the shelf tool created. I'm just going to click this button right here to disable it so we can see what our geometry looks like a little bit better. So this is looking pretty bad, but let's just go over some of what these settings can do for us. So if we're in our particle fluid surface, there's a bunch of things. The voxel scale is a pretty important setting. So we can actually change this, and you let it compute. You can see that it gets a little bit more defined. Now at this resolution, it's not going to do too much for us. We'll maybe run a cache and get a little bit higher res of a simulation that we can really illustrate this. But the voxel scale basically is when it converts the particles back into a VDB, what scale of voxels is it going to use relative to the grid that was used to compute the original simulation? You can see that that has to do with this particle separation. This particle separation is tied by a relative reference by default to that particle separation that we set on our flip object inside of our flip sim. So that's sort of what's going on here. So if you decrease this voxel scale, you're going to get a much more high-res surface representation, but it can only go so far if your simulation isn't actually that great, or that if your simulation isn't that high res in the first place, it's not going to give you good results. The other cool thing here is the influence scale. An influence scale kind of is, I like to think of it as like how metabolic is it working. Like if I bring this value down, you can see how this gets much more lumpy, and it's treating the particles more like they're little spheres. So really that's what this influence is. If I bring it up to a value of 6, it will generalize even more. It takes longer to compute, but you also lose some detail if you go too high with it. So this is sort of a balancing act right here. And again, droplet scale, if I increase the droplet scale, you'll see actually thicken up the liquid a bit. And so really we're kind of doing this balancing act, maybe bring the droplet scale down a little bit. You can see that my computer's really thinking about it's really thinking hard about doing some of these surfaces while everything is running. Again, like surfacing can take longer than the actual sim did itself, but this is now looking vastly different from what we had before. So maybe it's it's an exercise in decreasing your voxel scale, your droplet scale, maybe playing around with your influence until you find a setting that you like that works good for your situation. And I see stuff like this where it's a little bit jagged. I almost feel like I could bring this down to something like 0.25. I can already tell that for what I'm trying to do for this demo, that I just am going to want higher res geometry to begin with. But that's actually looking a lot better than it did when we first got started. Just by decreasing our voxel scale and really our droplet scale, we were able to like thin this surface out to look a lot closer to what we had originally. So other important settings on this node are the adaptivity right here. You can see how some sections of this surface have higher res geo than others. If you're doing stuff with viscous sims, it's computing all this topology differently every single frame. So having adaptivity on can cause flickering in your mesh if it isn't moving super fast. So a low speed sim like a viscous sim could end up looking really weird if you leave it on. So sometimes I'll just bring this all the way down to 0, and you can see that this grid is much more evenly distributed and much more high res. If you crank adaptivity up too high, you get a super coarse looking, it's very coarse looking fluid. So just something to be aware of with that sitting right there. I'm going to bring it back down to 0. This ISO value does like an ISO offset to expand or contract the fluid surface. So I'm just going to set that back to 0, but that's also good to note. And then another important section here is the transfer attributes. So what the surface is doing is it's actually taking these particles, and what it's doing inside of here is an attribute transfer like we've done before, and putting our attributes back in, baking the attributes into the individual points of our surface. So to illustrate that, because we had velocity on these points, hence we got these colors representing that, it's going to transfer those attributes back to this surface. It's going to transfer all the attributes that are in this little section right here. So if I just throw down a color, just to illustrate this, wire it in, I'm going to set the color as a ramp from attribute, and the attribute is going to be V. And now you can see that the velocity attribute is showing up in here, but because it's actually velocity is a vector, we're getting all this different color here. So if I actually go up here and throw down a VOP, a point VOP, and I'm just going to jump inside of it, and what we're going to do is just take the length of V, which gives us our speed. So I'm going to bind export an attribute called speed, and we're just going to measure the length. The length of the speed vector, or the velocity vector, will give us a length, which is speed. And now if I go to our color attribute and type in speed, you can see we get a black to white value based off of how fast the geo is moving. And if I go back in the middle here and select this nice blue color here and another blue color down here, we're pretty much back to where we started. If I change this range to 10, I think we set it to 10, something like that, we're pretty much we're pretty much getting the same color back. So that's just, this isn't necessary for this point, but it was just to illustrate that, we are able to transfer some of these important attributes back if we wanted to do any additional coloring or texturing on our surface with this node. So other cool things in here are filtering. Filtering allows us to do additional dilation and erosion and smoothing. So what by default it does here is when I click on this dilate, it actually dilates by 2 voxels and then erodes it by 2 voxels, so that we could actually dilate it, do a smoothing operation between, and then erode it back down. And sometimes this can help you get rid of lumps in your simulation. There's other smoothing options here we can use, and then there's these masking options. We could actually mask off certain smoothing operations by using different attributes in our sim. Cool. So I'm going to turn that off right now, and then the other one I want to look at is regions. Some of these are handy, like if we have a very large sim and we want to just we just want to focus on surfacing a part of it so that we can iterate faster. We can actually use a bounding box. It will turn on a bounding box for us. By default, the bounding box is gigantic, so I'm going to hit escape a few times. Yeah, you can see that it was actually trying to compute a bounding box that was 50 by 50 by 50 and then do some calculation with it. I'm going to just switch this to manual mode so that it doesn't update. And then I'm going to jump in here, turn bounding box back on, and change it to 1 by 1 by 1. So now if I go back to auto update mode, it have such a hard time computing that SDF. You can see now that we're able to focus this bounding box around a region of our sim that we want to be focusing on. My computer's super laggy right now because I think due to the recording and everything like that. So yeah, if we wanted to focus on surfacing this area right here, we could do that. I'm just going to turn it off. Another thing that can be super handy is if you have a camera, you can bring that in here and it'll actually clip off areas that are out of frame, so that you aren't actually surfacing extra particles that you aren't even going to see in your view when you go to do your rendering. So that's sort of just a quick overview of what the basics of a flip sim are. So just to kind of like finalize this thing a little bit, I'm going to do a couple things. First off, I noticed that my gravity in my DOPS, or my flip sim right here, is set to negative 0.98, and I want it to be 9.80665 because we were messing around with surface tension earlier, and I just decreased that value temporarily to kind of show what was going on. So if I click play now, the particles come down and then they kind of smash out. We get much less, that variable viscosity is a lot less obvious at this level. It still looks kind of cool, but I want to create it a little bit chunkier. So I'm actually going to go back to the source, and I like to go back to frame 1 and then go into the source, and over here with our variable viscosity, I'm just going to dive inside and set this fit range up to a new destination maximum of 1,000. And I could actually promote this if I wanted to. I'm just going to middle mouse click on this and say promote parameters, so I could actually control that outside of the sim. Other things I want to control are maybe the noise. I'm not actually going to change anything, but to make it easier for myself to control later on, I'm going to right click and choose VexVop options and say create input parameters. So now when we're out here on our variable viscosity node, we've got a ramp that we can use to control it. We've got our maximum value here. And so we can adjust this maximum viscosity value outside here and change the frequency if we wanted to, so on and so forth. And so now I'm going to just go back to the flip sim. So diving inside the flip sim, click play, and it's falling much faster now. And we get these black particles are just falling off, but the white stuff is remaining super chunky. So I think that that's looking pretty good. So the only thing left to do right now is just to up-res this and then cache it. So I'm going to change the particle separation down to a much lower value. And all these values are very dependent on what the scale of your scene is. You always want to kind of balance what's going to look good from whatever kind of camera space you're in. So I found that a value of 0.01 seemed like it got a pretty good looking result for me without being too long to sim. So now I'm going to just jump back out here and go into the import fluid node, and I'm going to go to the compressed cache, and I've already set up a file name here. I'm going to set it to $hip/cache/$OS, so it's going to name it after this compressed cache, and then name it another folder after the hip name, and then save those files in like so. And I only want the range from 1 to 48. So I right click here and said, I said delete channels, and then just hard coded in 48 there, and then hit save to disk. And I'll be back when that is done caching. All right, so that's done cached now. I'm going to click load from disk here, and then we can just take a look at the surface preview. You can kind of see these particles here. Just for the first 48 frames, so I'm just going to set the frame range to 48 and just kind of scrub through here. You can kind of see it's super splashy at higher res. I think if I was going to do this again, it was a 5-minute sim. I don't feel like waiting for it again. This is just a simple example, but I could crank up the lower level of the viscosity by modifying that output range in my VOP.net. And maybe get like a slightly less splashy, but we're getting this like nice kind of clumpy, chunky look at the top here, which is kind of cool. So that's just sort of something that you get with doing a variable viscosity sim. Let's just go and see what we get when we go out to like a frame like this and run a surface mesh on it. So now that we're out here, I want to modify this particle fluid surface because we had pretty high settings before, but now that we've increased the settings on our project or on the particles, maybe we could just not have to use such insane settings here. So I'm going to move these back to defaults. Before I click on this node though, I'm going to go to manual mode because it'll start cooking if I don't kind of manage that. So I'll go back to surfacing and we'll just choose a droplet scale of 1 and a voxel scale of 0.75. These are the defaults. I'm going to leave adaptivity to 0 for right now, and let's just click. I'm gonna put the display flag on the particle fluid surface and click this force update. And I had to switch it to auto update because I had an auto save that occurred in the middle of it and it kind of messed things up. But you can see here now we've got a much higher res simulation, and so this is sort of what the results look like. We get this like kind of goopy, chunky stuff happening up at the top, and all of these kind of drippier areas down here. So this might be where you'd want to start messing around with your smoothing settings and filtering and getting everything to look all nice the way we like it. We'll do a lot of that in the real example that we go through later on in this chapter, but just wanted to kind of give you an overview of what this whole workflow kind of looks like from a really generic, general level. So the next thing I want to do is let's just look at a different type of setup. So if your nodes are not already hidden, and I tend to like to hide all my nodes while I'm working so that I don't accidentally have hide or ghost other objects on. If I had ghost other objects on and I was inside of, my particle fluid surface or whatever, it would still be, and it was displaying my flip sim, it could see it start cooking, and it can lead to all sorts of bad stuff. So I like to kind of turn my nodes off a lot of times when dealing with sims, and then explicitly look inside each one when I need to see what I need to see. So now that being said, moving forward, I just want to make sure they're all turned off. So you can just select them all and hit the display flag. And then hit escape if it starts cooking. So I just turned them all on and then hit escape real quick because it was starting to calculate something I didn't want it to, and I'm going to do it again like so. So all my nodes are turned off here, and I'll just put it in a little net box that is called emit from object. So the next example I want to explore is how to get it to emit continuously from an object. So we're going to use another shelf tool. But before I do that, I want to create a new .NET. This is going to be the DOP network, like so. And the reason why I'm creating a new .NET is so that when I use the shelf tool up here, when we go to particle fluids, when I use this shelf tool, it actually can, it'll actually hook up to this network. If I have, so by default, flip sim is selected. If I were to use the shelf right now, I'd start adding things to my old flip sim because down here in the lower right-hand corner, flip sim is what is activated. I just want to activate my .NET 1 so that now every time I do anything off my shelf, it's going into this .NET. And I'm going to name this .NET, we'll call this flip emitter. And we're going to just do another shelf setup with let's do a sphere this time. And we're going to use the sphere as our emitter. I'm just going to bring it up a little bit and maybe, actually, for this one, I want to actually set its position from within SOP. So I'm going to actually move its translate back to 0. I generally like to position things down here on the SOP level because it seems to be less buggy when I'm trying to get things the way I want. So maybe I'll bring this up to a value of 4 and maybe scale it down to 0.5. So now that I've got that, what I'm going to do is go over here and I'll select the sphere and then say emit particle fluid. So it says fluid object to emit into. If any, there isn't any fluid object in our flip solver that we created just now. So I'm going to hit enter, and it creates. You can see it creates a new flip solver for us. And of course, again, it is huge. I'm going to hit the D key and set my background to dark. Again, by default, it creates this, it looks like 50 by 50 grid. I don't need that. I'm going to do another, let's do 5 by 5 by 5. And I'm actually going to bring this up by 2.5. So it's resting on the ground. And then we can just emit into this box. If I go up to the flip fluid object, I can actually close the boundaries as well. And this will like behave like a tank like we were talking about. So that's good. So if I hit play, nothing happens. You can see the particles are starting to kind of form there. That's just reseeding happening and emission at the same time. But we need some gravity, so I'm going to throw down a gravity force. Put that right here, right after the merge, right before the output. Now I'm going to click play. You can see that it is emitting our particles that go into this tank and sort of splash around, and then it just starts to fill up. Now it's pulling back really fast, so I'm going to hit the real-time toggle here, and maybe I'll just increase the range of our animation again by dragging this little triangle back out, or you could just set it to 240 over here. But if I let this play out a little bit, you can see that it just it's emitting like a faucet into our scene. So sometimes there's going to be instances where this is the type of thing that you're after. If you only want to emit for a little bit of time, you can, obviously shut that off. But in this setup, what it's done for us this time is it's created some more nodes. These two right here, the particle fluid and fluid interior, are the exact same as the ones that we had over here. So if we dive inside here, we've got a similar setup for surfacing. Don't need to worry about that, but I'm just going to name it import fluid emitter, and then this one is going to be fluid interior underscore emitter, and I'm going to call this sphere, I'm just going to call this emitter. And I'll just line all these guys up by holding down A, selecting all of them, holding down A, and then left mouse dragging down, and that lines them all up for us like that. So let's look at what it's done. Now, in the emitter, it's created an additional setup inside of them. We originally just had a sphere here, but now it's created this flip source for us. This flip source is doing a couple things. If we middle mouse click on here, it is creating particles. You see we've got a particles group here, and it's also making a surface VDB for us. You can see that represented in the viewport right here. So it's actually creating the surface and inserting it into the volumetric simulation of our flip, which is cool, but it's also providing the particles. So if I hit blast, if I throw down a blast node right here, you can see that, oops, I'm gonna wire the blast in right after this create surface. And if I select the surface and delete the surface out, you can see that it's actually creating particles here as well. So if we go to this create surface node, you can see it's got a few settings. The voxel size here, which is tied to the particle separation in our flip sim that it created, a shell thickness, and then it's set to create particles. And all of these particle separation and jitter values are all sort of bound to the settings that are in our flip fluid object here. So if I change the particle separation, the emitter, if I drop the particle separation down to 0.05, the emitter updates and creates particles in this dense manner as well. So good. The other thing is now we don't have an actual input type. It says input type surface SOP, cool, but there's nothing in the SOP path. That's because it's actually getting its particles from this volume source over here. So if we select this, you can see the volume source by default is bringing in volumes and particles, which are the two things we need for a flip sim because it's a hybrid. You can see it's set to source flip here. This is where it's actually grabbing our emitter out surface null that it created back up here in our emitter. It's looking at this node right here. So whatever's going into this node is what's being emitted over here in our volume source. So what I'm going to do is actually switch to my quad view real quick. So in my quad view we went over in a previous lesson, but I'm just going to throw that down. I'm going to hit the D key, set the background back to dark again, and I'm going to hit spacebar F down in this view and spacebar F down in this view. And in here I want to be looking at our flip, and in here I want to be looking at our emitter. So you can kind of see now the out surface, it's grabbing this node that's going right there, and it's grabbing this surface volume. It's set all that up for us, and it's also creating particles here for us, which is cool. So with a setup like this, additionally, we can add some additional attributes to these particles before they get to the out surface here. So, you know, for example, this is emitting like in a very regular pattern, but if we wanted to add some, you know, noise to the velocity so it was kind of more spraying out in a more random like way, we could do that here as well. So let's just throw down a randomize. We're going to do attribute randomize node. And if I just, if we go over here and select this node, you can see that, well, we can only really see our surface. So maybe for the time being, I'm just going to temporarily wire this blast in between so we can see our particles. And it looks like what it's doing, I'm just going to say hide other objects. So you can see it's creating a bunch of random colors. We don't want to do that. We just want to create a random velocity. So we just type in V under the attribute name. And then if I turn on these trails, you can kind of see that we've got all these little trails indicating the random velocity that we're supplying. I actually don't want to use an attribute randomize at all. I wanted to use a attribute noise. So because the randomize is 100% random, it doesn't get as good of results. So I'm actually going to wire in the attribute noise and delete the attribute randomize. Apologies. So here, instead of randomizing color, we're going to randomize velocity. And now you can see we get this nice kind of wavy pattern in our velocity trails. Maybe all I'll do is hit the D key, and under the let's see, guides, I'm going to just scale my vectors up a little bit so it's a little bit more obvious. So I'm scaling my vectors up to 10 so we can see the different velocity that it's adding in here. And now the actual velocity that it's creating is not centered. It's from a value of 0 to 1. So I'm just going to click this button to center the noise. So it's now kind of pointing in all different directions. And now if I start to mess around with the element size, that makes like higher and lower frequency noise. And you can kind of see that appearing in our scene right here. So now that we've created this noise on V, I can actually animate it. If I don't animate this noise and just go over here and click, I'm just going to hide the trails for a second, but I click play, not much is happening. I guess what I could do is probably increase this amplitude. So I'm increasing the amplitude of the attribute noise, and let's go back to frame 0. And now you can see it starts to push out initially, but it doesn't really do much after that. Once gravity takes over, it all sort of kind of it becomes a little bit more interesting, but it's still pretty uniform. But just to drive the point home, let's just crank up this amplitude to something like 20 so we can see what that does. Let's jump over here and click play. You can see water splashing out in all sorts of different directions. But that direction, I mean, this generally looks pretty chaotic so far, but we're getting these continuous streams that are kind of coming from these different areas. So if we wanted to modify that, you can see it almost looks like a bunch of holes were popped in something. And like we've got this arc up here that isn't actually moving or anything like that. It's just like continuously shooting outward this way and outward that way. We could actually animate that noise by turning on this animated option right here, and then we've got a pulse duration. This pulse duration, shorter values mean that it's just going to animate that noise faster, so we can visualize that right here. If we look, if I'm going to hit the D key, maybe bring the scale of these vectors down a little bit. So while I'm just in this attribute noise and I've got my scene set to hide other objects, we can kind of preview what that animation is doing by looking at those vectors animating around. So decreasing that pulse duration to something like 0.1 is going to cause it to frenetically, or I don't even know what the word is, frantically, just changing that noise pattern every frame. Whereas if we go with the longer pulse duration, those noises change at a much slower rate. Now it's reseeding, it's randomizing the pattern every frame, so we get a little bit of jitter based off of the point position, but in general, it's you can see the overall motion of it is much slower when we do stuff like that. So let's bring the pulse duration down to something like 0.2, 0.3, something like that. So now when we jump over to our sim, just select a node here, and I'm going to turn off the velocity trails and click play on this. We should get a nice, like, kind of undulating pattern that's coming out. So if that's what you're after, that's kind of how you can do that kind of thing by modifying the properties of your emitter, which is pretty cool. And you could have it emit variable, dense viscosities like we did as well. You could put a noise pattern in there to mess around with those, and you get different clumps coming out. Very fun stuff. So another common type of setup that we do is a tank setup. So I'm just going to show how to do that real quick. So let's just grab all these nodes, and I'm going to turn the display flag off, and I'm going to select them and put them in a net box, and we're going to call this flip emitter. So that's the emitter setup. This is the emit from object setup, and we can just create a new setup over here. And to do that, again, what I'm going to do is just create another DOP network, and I'm going to call this our narrow band. So this is our narrow band flip narrow band sim. In narrowband, basically, instead of filling an entire tank up with liquid, what we can do with narrowband is it'll actually just fill the tank and only analyze a certain distance from the surface, so we're not like kind of simulating all these particles inside that we don't need to and using all these extra resources. So to create this, I want to make sure down here that my narrowband sim is selected, so that when I use the shelf tool, it generates nodes that are being fed into this narrowband simulation. So now let's create a narrowband simulation. If I go up here to my particle fluids shelf and I create a flip tank and just hit enter, it will generate a flip tank for us. So it's created the volumetric bounds, which is good. And then it has created this fluid inside. So let's just organize these here. We get our fluid. This is going to be our fluid import. We get the same nodes here for surfacing that, which is good. I'm just going to call this import narrowband. And then this one is going to be narrowband or fluid interior narrowband. Both things that we have gotten before from these setups. The new thing about this setup is what we got up here in our flip tank initial. I'm just going to call this narrowband source. So let's take a look at what's going on inside this node. It's doing some cool stuff. So in here we've got our merge collisions. So if we had any collision objects, they would be merged in here and subtracted. We could subtract them. So if we had a boat in our scene, for example, we could merge that in here in our object merge, and it would like subtract out the hull of the boat, so it wasn't sort of in this simulation initially. And then we have this thing called the wave tank, and the wave tank has got a bunch of green on it, which means it's all hooked up to our DOP simulation. So I'm going to bring that up over here. Now we're on our old flip emitter. I need to back out and go into our flip narrowband sim here. And so here we are. We've got our flip tank object right here that's being wired into our flip solver now. And you can see this particle separation is tied here. We've got oversampling set, which is probably tied to the particle motion oversampling right here. If I click on there, you can see, yeah. So there's a bunch of settings on this wave tank, which is part of the Ocean toolkit, to create this sort of narrowband sim over here. In the flip solver, it's actually created under this narrowband tab. It's enabled particle narrowband, and then we can set the bandwidth. If we go over to this wave tank, you can see it's set to create particles here, and we can actually set the water level. So the water level is set to, it looks like 0. So those are just things that are important to note. There's also these other settings that I don't think are necessarily You know, it's a flat tank or an ocean tank. Most of these we don't really need to worry about at this point. We're just interested in getting those fluid particles into our sim. So now, if I go back and hit spacebar 1 to get perspective view back, and I dive into this flip solver right here and click play, we get a little bit of this stuff happening down here. That's, I think, just the narrowband calculation doing its thing, but nothing is happening with this liquid. So let's create an object and drop it into the liquid. I'm going to go up here and I'll create a collider object. So let's create a geo, and the geometry, we'll call this a collider, and let's just jump inside. Oh, it looks like it named it collider 1. That's fine. It's because I have another collider over here named collider, so it's just going to change the name if it sees the same node. So I'm just going to get in here and let's create, let's do a torus. So torus is going to be our collider, and let's just actually, I'm going to jump in here and let's maybe bring the torus up a little bit, and then we'll give it a little bit of rotation. So it's kind of at an angle. I think maybe also we can bring its overall radius down. This is sort of like the radius of the, it looks like the radius of the ring itself. Oh no, this is the radius of the ring, and this is the radius of, well, the radius of the, so this is the radius of the sweep, and then this is more or less the radius of the ring. So this will be sort of like maybe like an inner tube that we can drop in there. Cool, so that's good. That's in a good position. So right here, what I could do is, instead of actually, you know, going up here to my colliders and saying deforming object or static object, I could actually go up here and create a rigid body out of this. So let's call this our, we're going to use the shelf tool that's called RBD Hero Object. So let's click on that. And what that has done is, if we go over here into our flip sim, you can see that it's actually added a collider RBD object here and a rigid body solver. And then the rigid body solver is wired into this merge. So we've got two solvers in the same scene right now, which is kind of crazy. Whoops, didn't mean to click on that. Yeah, if you want to be scared of something, jump inside the flip solver and look at what side effects is set up for you, so you don't have to. I mean, all these crazy nodes are feeding into create those fluid simulations. And you look, it's probably organized. You can see this is the solve section. What is this? This is the volume setup, and this is the particle setup. So you've got your flip, you've got your volume calculation, and your particle calculation. Anyways, so yeah, it's cool. We've got this rigid body solver and a flip solver. So let's just see what we get when we hit play. In here, I'm going to hit play, and nothing happens because there's no gravity in the scene. So let's add a little bit of gravity right here after the merge. That gravity force will apply to both the rigid body and the tank. So let's go back to frame 0 and click play. You can see that the donut falls in and exits the narrowband, and basically is no longer affecting the sim. It just continues to fall. But you can see what narrowband's doing is it's actually generating particles that are near this collision and allowing them to have an effect with the water up to a certain depth. And this is much more efficient than the older way, which was we would have filled this entire thing with particles, and then it would have taken a lot longer to sim. So this is really cool. We've got this highly efficient narrowband setup, which is really great. But our inner tube is just sort of falling through and dropping out and going on forever and ever. So one of the ways that we can actually apply a little bit of feedback to this rigid body is we can do that using our flip solver. The flip solver has an option on the, I believe it's under volume motion, and under the solver section, there is this feedback scale. So if I bring that feedback scale up to something like 2, and then we click play again, you can see the sim runs a little bit slower, but now this inner tube actually collides with the water and is pushed back up and wants to kind of come to rest on that surface, which is pretty cool. So that's kind of a way that you can create like kind of kind of a floating object if that's what you want to do. A lot of times what I'll do is I'll actually just animate a floating object and then sort of like actually just make a one-way interaction and just have the floating object be a static collider. But this is a really cool way that you could actually like combine a couple different areas and get that kind of two-way feedback, which is great. An inner tube, sweet. So this sort of wraps up all the things that I kind of wanted to talk about in the intro and theory section of this flip chapter. So in the next lesson, what I want to do is actually dive into doing a cool effect where we morph some text between between two different pieces of text, and we like super art direct our fluids using one of my favorite features of the entire fluid setup, which is the suction force. The suction force will allow us to really just get exact control over where our fluid particles are moving and giving it this really nice organic motion at the same time. So stay tuned for that lesson, and I'll catch you in the next lesson.